So, hi, I'm Fred. I'm the Chief Architect here at the Spark Technology Center, and tonight I'm going to be talking to you about what's new in the Apache SystemML project. So, a little bit about myself to start out. I came here from IBM Research, where I worked for 9 years. Prior to that, I was a grad student at UC Berkeley, working in databases. And it's been a great time working at IBM, but it's really exciting to be working at the Spark Technology Center now. And the final thing is I am a SystemML committer, so I'm a member of this project that I'm going to talk about today. So how many people here are familiar with Apache SystemML? So some of the audience? Well, for the rest of you, let me answer the question that's probably foremost at your mind right now, which is, what is Apache SystemML? Now, the next slide, I have a nice animation, which is pre-canned and goes in exactly 30 seconds. So, okay, here we go. So, in machine learning, it's very easy to code up custom algorithms if you write them in a high-level language, such as R or Python. But when you get that high-level representation to run at scale, you need to rewrite the algorithm and make it go on something like Spark, which requires rewriting the algorithm, takes a lot of time, introduces errors. So what Apache SystemML does here is it automates that process of going from the high-level representation of a custom or semi-custom machine learning algorithm directly to a fast result. And this is IBM research technology, which is now inside an Apache project, a Apache top-level project as of about 2 weeks ago. So our website's at the bottom of this page, systemml.apache.org, and you can find that link again at the end of the talk. Now, by the way, I should note this is going to be a very compressed representation of what's going on in SystemML because there is a lot going on, but the slides will be available after the fact, and we'll have some great links in the end of the talk if you want to find out more. So that's the elevator pitch for SystemML. It's about taking high-level representations of algorithms and automatically adjusting them to the data characteristics, to your cluster characteristics, to make them scale. A couple more details about SystemML that we're going to need to know to understand some of the new stuff that I'm going to talk about today. The way that you express algorithms to SystemML is you use linear algebra, and the way that you use linear algebra should be familiar to anyone in the audience who is familiar with coding up in R or Python with NumPy. So here's a quick example of how you would code up an algorithm, and I'm going to do linear regression from scratch in 3 lines of code. So the least squares formulation of linear regression looks roughly like this if you write it down in terms of linear algebra. You want to choose a vector W of coefficients that's going to minimize the difference between the product of your training data, X and W, subtracted out from your labels. Okay, well, minimize the L2 norm of that, I should say, which you can factor out into this second line. Okay, if you take the gradient of that, when that gradient is 0, this is going to be minimized, which gives you this nice expression down here in linear algebra format, a system of linear equations. And you can, if you're coding in R, you can basically copy and paste this line of mathematics directly into your R program and simplify it a bit to make it easier to read, and you get 3-line script to do linear regression. You can do the same thing in Python. It might be a couple characters longer. So this is a really, really convenient way to take an algorithm out of a textbook or a paper and quickly produce a prototype script. And your prototype script will run great as long as the data is small, but then the question is, of course, what happens when you try to run this over large data, or over sparse data, or over funny-shaped data? Well, sometimes it works, and sometimes it doesn't. In the case of this particular example, that first line up there is the performance critical operation here. X is your matrix of training data. X is all of your training data. In that first line, we're left multiplying that matrix by its transpose. So if you wrote down this code in R or in Python for NumPy, you would have to make it so that the entire training data fits in memory twice, because you also need to store the transpose in dense format. So, like I said, it works great in some cases, but what affects is sparse? Well, then you need to switch over to using a sparse matrix library, which adds some lines of code, adds some complexity. Or worse, what if the X is so large that even if you encode it in sparse format, it's not going to fit onto one machine? Then you need to go back and just use these 3 lines of code as a reference and re-implement the algorithm. So this kind of re-implementing the algorithm, changing the data representation, these kinds of steps get very painful for data scientists who want to focus on the equations, focus on the math. And so this is the pain point that SystemML addresses by automatically creating the parallel or sparse version of the program and adjusting that based on the properties of the data and the properties of the available hardware to execute the algorithm on. So that is a very short introduction to the core of SystemML. I have a 30-minute version of this online on YouTube, and I can also give a 90-minute version of this if any of you want me to come and talk at much greater length. But I'm going to move on to new stuff. And just before I do that, let me bring up a couple points that are going to come up over and over again, because the chief benefit of the SystemML approach is basically summarized here. So because we're separating out that high-level representation of the algorithm from the actual implementation and automating that transformation based on characteristics of the data, that means we can greatly simplify developing that algorithm. You just write down the math. It also means that we can change the algorithm. You want to add some regularization, some custom regularization to your linear regression, or you want to change the loss function for factorizing your matrix, you can do that by just changing one equation. You don't have to rewrite a complex parallel algorithm. And third, and this is going to be the dominant theme in a lot of the stuff towards the end of this talk, as the system gets better, as our optimizer gets better, your algorithm doesn't need to change to take advantage of new functionality. So over time, algorithms get faster and faster without modifying the code. So keep that in mind, it's going to come up later on. Okay, so I think we've covered briefly what is Apache SystemML. Obviously, there's a lot more, but I'll give you some pointers to find out more information later on. But let's move on to the meat of this talk, which is what is new in Apache SystemML. So now I mentioned that we write algorithms down in SystemML using high-level linear algebraic formulations. Here's just some quick representations of how you would actually write an algorithm down for some future reference on the next couple slides. In SystemML, we have a domain-specific language. We call that DML when it has an R-like syntax, and there's another variant, which is underneath the same language, but has a Python-like syntax that we call PyDML. Here we have 2 implementations of Gaussian non-negative matrix factorization in the 2 dialects of the language. The key thing to see here is this is a domain-specific language. It has a whole bunch of linear algebra primitives. It has a lot of useful built-in functions. You can add new user-defined functions to it. But even though it looks like R or it looks like Python, it's not R, it's not Python. It's a much narrower subset of functionality that our optimizer can tune and automatically parallelize. So when you write an algorithm using this language, and you want to embed that algorithm in a larger pipeline or a larger application for scoring purposes, you need to take that algorithm, feed it through SystemML, and get back a function that you can call from a host language like R or Python or Scala or Java. And we provide a series of APIs to give you exactly that functionality. With SystemML, if you download it, you'll get the Scala, Java, and Python APIs, and there's a new project called R4ML, which is being incubated by the Spark Technology Center that also provides an R front end to SystemML. Now, in this application interfacing space, we have some new developments in the project. The key one is an API that we call MLlearn, which allows you to take an algorithm, a custom or semi-custom algorithm implemented with SystemML, and wrap it up in an API that looks like scikit-learn or the related API from Spark, ML pipelines. So we provide, along with SystemML, or we will with the next release, pre-wrapped algorithms implemented in our domain-specific language for some common regression and classification areas that you can take and modify or just use as example code to wrap your own custom algorithms. And this supports, since it's wrapped up in scikit-learn compatible wrappers, you can use all of the hyperparameter tuning and composition that you would normally do with a scikit-learn algorithm. Here's a quick example. of how pluggable it is. This is the example code for doing linear regression from the scikit-learn website. If we take this code and just modify 2 lines, and of course include SystemML's jar on your class path, actually import SystemML since this is Python, then you are then doing linear regression using a high-level algorithm that's compiled and optimized by SystemML. And in fact, if you have more data than fits on one machine, SystemML will run that algorithm spread across the cluster. And just by changing 2 lines. But you'll notice the parts in the bottom in red to actually fit a model, to do prediction, they don't change because it's the same API. Similar thing happens with MLlearn if you want to use the ML Pipelines API that comes with Spark. Here again we have the example code, this time from the Spark website, for doing logistic regression with ML Pipelines. If we take this code and change 2 lines, you can switch to a variant of logistic regression that is implemented in our high-level language, DML, and is optimized and customized for your data characteristics by SystemML. And like I said, 2 lines. Everything else, including how you fit the pipeline, how you can compose these stages together, it doesn't change. So that's a very nice way to access the functionality of SystemML, a great way for, I'd say, a chief data scientist to package up an algorithm for more broad production use. And in addition to allowing you to take these canned algorithms, you can plug in a custom algorithm here. And another thing that you can do with this API is you can plug in a deep learning model and have SystemML run that deep learning model for training or scoring purposes. And the tool that we use to do that plugging in is called Caffe to DML. This is a new experimental tool, still under active development, but a version of this should be in the next release. And basically what it does is you run a Caffe model file and the coefficients file through Caffe DML, along with some information about what do you want to do with this model? Do you want to train it? Do you want to score it? If you're going to train it, how are you going to train it? And that generates a script in our language, DML. And remember, our language has lots of facilities for doing linear algebra. And deep learning, when you get down to it, is just linear algebra. So we can take very complex models up to the scale of like a ResNet and generate a script that will train that model. And we run that through SystemML. As an added bonus, the generated script will produce TensorBoard compatible output. So you can actually use the TensorBoard tool to monitor its training progress. And again, it's a script written in terms of our high-level language. So as our optimizer gets better, that script gets faster. The other thing is that script, you might think since it's generated code, it's going to be kind of incomprehensible. But actually, these generated scripts turn out to be quite easy to read because the code that Caffe to DML generates in our high-level language DML makes use of here's an example before we move on of how you call that. You just pass in your Caffe files, and then you get back essentially a pipeline stage that is the model. So as I was saying, this generated code that happens inside of here takes advantage of our NN library. This is a library that was written primarily by one of our developers here at the Spark Technology Center that provides a whole lot of deep learning functionality entirely written in our high-level language DML. Because it's in that high-level language and we don't need to provide like GPU implementations of individual operations, we can add new functionality to this library really fast. And this is what we've done in less than a year. This is continuing to move forward quite rapidly. You can see a link down there to the GitHub for the core of that, and this will be included in our next release. So here's some examples of creating a deep learning net using that library. As you can see, it's a lot like TensorFlow. You know, subroutines to build up the graphical structure. And again, since this is high-level code underneath, these functions are just expressions in linear algebra if you drill down to the source code. Since it's high-level code, this gets faster as the system moves forward. And in particular, it's getting faster and faster as we add GPU support to our backend. So in recent builds of SystemML, we have been adding a GPU backend to SystemML. Now I say backend because you see we have in SystemML, remember, we take a high-level representation of an algorithm, we automatically turn that into a low-level plan. That low-level execution plan runs on our runtime. That runtime is actually a pluggable quantity. So we have 3 different runtimes. We have one for running on single node in SMP mode. We have one for running just on Spark, and we want to have a hybrid of the two. That hybrid is our default mode, where the optimizer chooses whether code executes on the master node or across the cluster in parallel. So, and we're using this pluggable API to add a new GPU accelerated backend to SystemML so that we can take advantage of GPUs in several different configurations, either a single GPU on the single node execution, multiple GPUs in one machine, or GPUs spread across a Spark cluster. And the idea here, again, coming back to what I was saying earlier, remember this slide from before, is your code gets faster as the system improves. So as we add more and more to our GPU backend, you basically GPU accelerate every piece of DML code that has been written without actually changing the code of the algorithm. So here's a quick snapshot of our progress. As you can see, the single node, single GPU version of this backend is mostly complete at this point. We're working on single node multi-GPU, and then in parallel also planning the fully distributed GPU support. But already with only a single GPU, we get significant speed ups on the order of 5 to 10x for deep learning use cases, but also we're getting speed ups for non-deep learning use cases because we just take this GPU acceleration and apply it to more traditional scripts. So that's a great example of, as the system gets better, your algorithms get better without needing to write a new line of code. Now, in addition to offloading code to the GPU, another thing that we're doing in support of deep learning, but also to make older algorithms, more traditional algorithms run fast, is code generation, aggressive code generation in our compiler. This is an extension of something that we have already implemented in previous versions of SystemML that we call fused operators. Now remember our linear regression example from before. We have 3 lines of code that implement linear regression, at least in a high-level language. And we have that key operation of multiplying the matrix of training data by its transpose. If you do that in that operation in terms of the basic linear algebra primitives, you'll need to transpose x and then multiply that transpose by the original matrix. That's 2 operations. They're both quite expensive. But actually, if you combine those operations together, you can compute that multiply by the left transpose much, much faster than you could do the transpose followed by the multiply. Basically, what you do is you take the dot products of all the combinations of columns in the matrix, which is something you can do with very aggressive use of parallelism on a single machine and in a single parallel pass across multiple machines. So fusing together operations into these complex kernels allows our optimizer to take the intuitive representation of an expression and instead execute an equivalent but much faster version. And this can make things actually asymptotically faster. So here's an example of an expression that occurs a lot in equations that you'd be running when you're doing matrix factorization use cases. This is best explained with a picture. So imagine you're trying to factorize a matrix W, which is a sparse matrix of your past observations, into 2 factors, U and S, say for a recommender system use case. Well, in the middle of the algorithm to do that factorization, you'll probably be evaluating this expression. And what that expression does is it multiplies the 2 versions of the factors together to produce this U times S product, and then multiplies that again, multiplies that cell-wise by your original values, and then multiplies that again by one of the factors to get you an intermediate that can be used to compute the gradient of the other factor. Now, the key thing to note here is typically this matrix of W, your original weights from your observations, is quite sparse, but U and S, the factors, are typically dense. So this matrix here is a very, very large, dense intermediate value, typically much larger than the original training data. And so if you compute this expression from the inner paren outward, it's going to require a huge amount of memory and it's going to go very slow. But what you can do is you can actually directly compute the output if you fuse all these operations together. And that's exactly what we do in SystemML. The optimizer, if it detects this kind of pattern, will replace it by a single fused kernel that walks through the blocks of W, computing the blocks of the output. And this is asymptotically faster. It's not just a constant amount. It actually can be faster by an arbitrary amount depending on W's sparsity. Now this is a very, very powerful technique that can make algorithms run 1,000 times faster. But there is one caveat that the optimizer, the component of SystemML that's automatically parallelizing programs, has only a fixed menu of these fused kernels and a fixed menu of transformations that will make a given expression match one of these kernels. So if you have something that's not on the menu, it's not going to get accelerated this way. Well, to remedy that, to broaden the applicability of this technique, what we have done is we now generate these fused kernels as Java code on the fly. And so the way that we do that is we start with the directed acyclic graph of high-level operations. This is our internal representation of an expression in SystemML. And we translate that down into an equivalent expression with some additional annotations that allow us to run some rules to transform the expression into a format with an order of operations amenable to code generation. Then we go and generate Java code on the fly to evaluate that expression multi-threaded or parallel and generate the same result, but much, much faster. And once we've synthesized that code, we generate a new operator which implements the fused operation, plunk that back into the execution plan, and move forward with compilation. So with this generated approach, if you look at individual equations, how long it takes to evaluate the value of expressions here. Here we have some little expressions at the top that we're actually evaluating. The generated code, which is the blue line here, the blue bar here, takes about as much, it runs about as fast as our hand-tuned, handwritten primitives. And when you fall back to the level of entire algorithms, entire scripts, we get similar amounts of speedups in some cases and better speedup in other cases. So here we have the execution time for Poisson non-negative matrix factorization. This is one of these matrix factorization algorithms that has that expression I showed earlier, where you have the large, dense intermediate. And so if you do not have operator fusion, it takes a very long time to factorize a matrix if you've written down the algorithm in its intuitive form. But with fused operators, it is much, much faster, asymptotically faster, as I would say, as I said, because you're taking advantage of the sparsity of your input matrix. With a generated code, we have a small constant increase in running time because of the cost of actually compiling that generated Java code. But you can see as the data size gets larger, that increase becomes less and less significant. Here are some numbers from another algorithm computing L2 SVMs. And you can see in this case, actually at the larger data size, our code generator is finding a new fused operator that we didn't have before that actually makes the algorithm run twice as fast. So already we can see the benefits of having the optimizer generate new fused operators instead of choosing from a fixed menu. So this is a really cool development. It is in our mainline code. It will be in the next release. And there's actually a research paper at CIDR this year, and there should be another paper coming up soon. Which brings me to the next topic, which is compressed linear algebra, another topic that we've been writing papers and putting code into SystemML for. The basic idea here is that when we have a lot of scripts, a lot of algorithms that we've written in our high-level language for not only so we can have a nice library of algorithms, but also so we can stress test our system. And while we were looking at across all these algorithms, we noticed something, that there's this very common pattern that occurs over and over again, that of repeated read-only access to a large matrix of basically lightly transformed training data. Here's a concrete example. This is linear regression by the conjugate gradient method. It's an iterative algorithm. It has this while loop on the outside. It repeats until it converges. And the performance critical part of gradient descent is typically computing the gradient. In this case, there's one input, x, which is your matrix of training data, and everything else is of such a small size that it's basically insignificant performance-wise. So the key to the performance of this algorithm is making this line run fast, which means doing repeated read-only access to x fed into these linear algebra operations. And this pattern occurs in a lot of other algorithms over and over again. So what we do here basically is we borrow some insights and some techniques from the database world, where compression is a well-studied technique for making queries run faster with less memory. Since a lot of this data comes from a database, or looks like it comes from a database, your training data, we can use a lot of techniques from database compression to make it smaller. And by being careful in our choice of techniques and how we combine them together, we can actually do operations, linear algebra operations, on the compressed data in the compressed domain, which saves us from the chief drawback of what would happen if you tried to just compress data with, say, Snappy, which is that decompressing the data takes a lot longer than most of the operations you'd want to do over the data. By operating in the compressed domain, we can make things very fast. In fact, end-to-end and entire scripts, you're looking at up to 26 times improvements in end-to-end performance in our experiments. So in micro-benchmark results, some operations, when you compress the data, they turn into metadata operations. So here we have the example of x squared, basically squaring every individual value in a matrix. If you compress that matrix in an encoding that separates out the distinct values in the matrix from the locations of those distinct values, then, well, squaring every value is a metadata operation. You only need to touch the distinct values. You don't need to touch their locations. And you can do that much, much faster. Here we have the time for that operation in the compressed, in the uncompressed data, and on data that's been compressed with our compression technique. So you can operate on it in the compressed domain. Blue is the normalized time to do the operation over each of these machine learning data sets in the uncompressed domain, and green is when you compress. You'll notice those certain lack of green bars. That is because every green bar except for the first one has a size that rounds down to 0 pixels. If we switch to a log scale, this is what it looks like. So except for the Higgs data set, which has a large block where we can't apply compression because of the way it's generated, these other common machine learning data sets compress really well, and we can square every single value in that data set 3 to 4 orders of magnitude faster than if we were doing it over a dense matrix or an appropriately sized sparse matrix for the sparse data. So that's a really powerful result. Now, obviously, not every operation speeds up that much, but even for operations that really, really need to touch the entire matrix, such as multiplying a matrix by a vector, as you would if you were doing stochastic gradient descent, we still can do those operations in the compressed domain in time comparable to how long they would run if they were over uncompressed data. And as a result of all this, we can take a script in our high-level language and execute it with the main input compressed, so we can fit like 10 times as much data in memory, or if we're reading it out of disk repeatedly, read it from disk 10 times as fast. And when you take this and apply it to entire end-to-end scripts, you get results like this. We took varying sizes of the MNIST data set, which is a generated data set of handwritten digits, and we ran the algorithm to do, if I recall correctly, to train support vector machines. And we ran it with uncompressed data. We ran it with compression turned on, and the overall improvement in performance here was about 5 times. And this is end-to-end. This is an end-to-end result. This includes the overhead of reading in the data uncompressed in both cases, and when we're using compression, the overhead of compressing the data on the fly. So that's a very powerful result. In some of our experiments, we were getting, for some algorithm and data combinations, up to 26 times faster. So, yes, there's a question in the back? The question was, do we use caching of intermediate computations based on heuristics? And I can give you a very long answer to that. The short answer is yes. And our system aggressively manages that cached data based on an analysis of the control flow in the script. So very good question, yes. But I'm running short on time, so I'm just going to wrap up here. We can have some questions immediately after the talk. So I talked about a couple of cool new things happening in the Apache SystemML project. Number one, we are the top-level project, Apache SystemML now. We have graduated from incubation. We've made significant improvements to our APIs for running high-level scripts in our high-level language. We've added support for deep learning, both in terms of APIs for running deep learning models or for training deep learning models, and GPU support for training them faster. And we've also got code generation, which helps not only deep learning use cases, but more traditional machine learning use cases, and compressed linear algebra to make operations run order of magnitude end-to-end faster. Now, if you download the latest version of SystemML from our website, which is 0.14, you'll get some of this functionality. If you wait until this summer, when we will be releasing SystemML 1.0, you'll get all of this stuff. This will be our first release as a top-level Apache project. You'll get the API improvements, an improved version of deep learning, code generation, dynamic code generation of fused operators, and compressed linear algebra is now turned on by default. So that's a summary of the really exciting stuff going on right now in the Apache SystemML project. If you'd like to find out more information about this project, our website is systemml.apache.org, and I have a couple links here to much more detailed information that you can download papers from. These slides will be up online, so you can get the links off of the slides. Anyhow, thank you very much for coming to my talk, and I'll be happy to take any questions at this point. So we have Brave Soul with a question. I know I went very fast through that, which can be a little intimidating, but yes, please.
So can you speak a little bit about industry adoption? Do you see customers trying this? What problems they encounter? Basically, I think it's a great high-level way to introduce data science communities. Obviously, R is predominant and Python.
Yes.
How do you see adoption of this going? Do you have any kind of feedback from industry?
We've been working with a select number of different groups inside and outside IBM to try out the system, and everyone that we work with has been very helpful in tuning it. The primary use at this point has been in IBM products, but we're very eager to collaborate with outside adopters of the system. And you can go to our website again and subscribe to the mailing list and see the traffic there, and post to the mailing list if you should happen to download our release and try it out. I would encourage people to try out the project and contribute to it, because we're really trying to build out that community. Additional questions? If not, then